Hey everyone, it is December 17th, 2019. Time is about 11:30. It's 46 degrees Fahrenheit out, and it is Geo-Rant time, Geo-Rant number 115. Now, what I'm doing here is this is actually an introduction to a Geo-Files episode I am doing, which will be linked below once it is edited. It has already been recorded. But the reason why I'm not including this in the Geo-Files episode is because it's way too long as it is. I don't want that Geo-Files episode to be a feature-length film. And it was getting there, okay? So I'm going to do a couple of Geo-Rants. This is the first one that is going to be an introduction, a background to the Geo-Files episode. Anyway, before I digress too much, what are we talking about? Well, I'm going to talk about relative and radiometric dating and how the two complement one another and what would happen if they didn't. But first, I got to show you a geologic map. This is just a little strip map I made, okay, right here. You can see I have a north arrow and it's in its horizontal scale because that's what you do. You always do that on geologic map. And you can see these little T's here with numbers are my strike and dips. I've gone over those before. And there is right here, a little circle with a cross in it. That means that is a strike and dip that's a dip and strike. It's a dip of 0, which means there's no strike. That's our symbol. It is a strike and dip. It means horizontal bed. And here we have a fault. U is up, D is down. We are going to take this and generate a cross section. This is our map view. So with no vertical exaggeration, we are going to develop a cross section, and we'll say for the sake of argument and simplicity that we have four wells that are right along our traverse here that are going to perfectly line up so we can generate a better cross section. We are going to use our strike and dips as well to generate our cross section. And so we do, and this is our slice into the earth. This is our cross section. Don't worry about the colors for now or the geologic units. I will get into those when I do the stratigraphic column. So here's our map view. Here's our cross section. Here they both are, so you can see them, okay? So we've used the available data, and we've used stenos for basic laws, which I'm going to talk about in another Geo-Rant, to draw this cross-section. And these wells kind of verify that that's legitimate, all right? So subsurface exploration, we use stratigraphic laws to generate things like this along with field observations, all right? So we generate our cross-section. If our stratigraphic laws were not valid, when people put water wells in, they would see something totally different than our cross section. And I've gone over this before. This is one of the ways geology makes a prediction, okay? And I've done that with an ore body in a previous rant, I believe it was. Not too long ago. You can go through the list and find it. I'm not linking it below. Okay, so we take this, and using the laws, basic laws of stratigraphy, we come to the conclusion that our yellow unit is our oldest. Our green unit is our second oldest. It's kind of greenish there. All right, our blue unit is what is younger than our green, and our orange is the youngest unit. Sedimentary unit, these are sedimentary units, and then a fault occurred, and then this is an igneous intrusion. This is our last unit. So we have 5 geologic units exposed. Well, so we make a strat column. We do that, and this is the kind of stratigraphic column you're going to see in a field book. All right, this is what you draw. Stratigraphic columns are just a graphic representation of the lithology of your map area, essentially. You don't extrapolate these and correlate these on massive scales. The most you might see them is a state scale or generalized, and they'll be very generalized, or provincial scale, also very generalized, and they leave things out. These things are meant to be local examples of what you're doing. Okay, you can't extrapolate this across the planet. Right? That's not how geology works. All right, but before I digress, so relative dating, the yellow was a sandstone. A green is a basalt, and say we have an actual date. This one, that red X, that's where it's taken from. We have an actual date, okay? And we know this is a surface flow because it's pitted on top, and these squiggly lines here are a baked zone. You also see a baked zone along the gabbro. Then we have a slate that's conglomeratic and sandy at the bottom, and that's going to come in key when we take detrital zircons, and it's sandy up here. And here we have a dolostone that is also sandy at the base, and the whole thing is cross-cut by our gabbro. Now we don't have our fault on here. Why? Well, because it's not necessary. We don't have a repeat in units where we expect the fault to actually have influenced this, because it all post-dates this. Well, at least post-dates up to the dolostone anyway. So that's not necessary. Sometimes you will see faults on a stratigraphic column. Now, usually on a geologic map, your stratigraphic column is going to contain boxes with letters and or numbers in them with a formal geologic name. I am not doing that because I'm not going to make this longer than necessary. I'm just giving you the lithology and showing you what you draw in your field book and adding the colors from our map and our cross-section. Okay. So this is our relative dating based off our 4 principal laws of stratigraphy. So I go and I want to know dates. I go and I pull a bunch of detrital zircons, which are the green, and one from the gabbro, which is red here. Okay, so I've done that. All right, and as you can see here, detrital zircons, remember, I've said this before, you cannot be older than your youngest zircon in a sedimentary rock. And the reason for that is sediments are derived from other rocks, which means they carry the zircons from other rocks. You cannot have a zircon in a sedimentary rock if the rock that it's derived from did not exist. So that's what these are. These greens are youngest detrital zircons found in those specific layers. As you can see, you get 2 different ones, but this is the oldest part of the slate. This is the youngest, so there's no problem there. Actually, this method is a way to time source areas. You can also get from detrital zircons, you can't get an absolute date, that doesn't happen, but you can get source area, because the ultimate source of these zircons are some sort of crystalline rock. Okay, so you can get a source area, and like the slate here, we have 1113 plus or minus 5 MA. That would tell us, and say we had a granitic intrusion just outside the area that is 1,113 million years old, we would know that is our source. MA is millions of years. Actually, here you can see I put it up here. It actually means mega annum, which is millions of years ago, or just millions. Okay, that's how we use it in geology. And so based off of these two, and here you can see it sideways, I hope that sun, I have to do this during lunch, you can see, all right, that they correlate really well. All right, now back to our relative one, what we do here is we attached geologic time to our strat column in order to get a sense of deposition. And here we assume, based off, and this would be based off published literature or other rocks in the area that we have done, that we have a late Mesoproterozoic rock here. We have a minor unconformity here, a big one here. We have early Neoproterozoic rocks up here, and we suspect the gabbro is Cambrian. Now, we dated the gabbro. That is not Cambrian. It is Neoproterozoic. So we've gathered new information to add to our model, and this becomes our new time scale attached to our stratigraphic column over here. What happened was we refined our knowledge, and the two complement each other. Nothing here violates the laws of stratigraphy from the dates. If it did, and I'm going to give you an example of how that would occur, that either means our laws of stratigraphy are incorrect, our dating methods are incorrect, or they're both incorrect. And what we already know from our relative dating in this case, and our radiometric dating, and our verified cross-section via wells, that's 3 things that support one another. They do not contradict. All right, so we have an accurate model of reality. We don't just toss it to the side for the sake of tossing it to the side and make erroneous unfounded claims and arguments. And I've said this before, and I'm going to keep beating this dead horse because it's important. Arguments are starting point in science, all right? They are not hypotheses. They are not theories. Analogies are not even included in scientific papers because they are only meant to help you understand a concept by association, all right? And they are not meant to be extrapolated to the nth degree, and that's what people do. Earth creationists. That's not their point, okay? So, all right. So how would we know? How would we know our methods are flawed? What would we expect to see if radiometric dating or our laws of stratigraphy were invalid, okay? Say we got these numbers. Green is still detrital, red is still our igneous, undeformed igneous units. If we got these kind of numbers, using Steno's laws, we would be forced to make a stratigraphic column something like this. As you can see, the sandstone is up here. It intrudes our slate and our gabbros. That is not physically what we observe in the field because these things are all tied together. In the field, we observed a bake zone, which means the lava came over it and cooked it. And we have a pitted zone on top, no bake zone here. So that is a strong indication that this is a surface flow and not a sill. But based off these crazy dates, I would be forced, using the laws of stratigraphy, to come up with this model, which does not compute. It doesn't make any sense. And spoiler alerts, here, I'll show this sideways. Guess how many times this has happened? I'll give you a hint. 0. Okay? Now, until something like this happens, there's no reason to throw uniformitarianism into the garbage. And something else about uniformitarianism before I stop this here. It does not mean every single thing in geology happens very slowly. We know that's not true. We identify impact craters. We identify storm rip-ups. These are obviously single events. We know a fault can propagate from a single earthquake. So, yeah, it's neither here nor there. But anyway, that's it. If you have any questions or comments below, please leave them, and I hope you learned something.